Hi, algebra fans. Mrs. Lindsay here. I was watching many of your videos this weekend, and it was a lot of fun. So I thought I would make a video for you. This is my favorite topic ever, cubic functions and their roots. I love cubic functions. There's so much going on with cubic functions, and not just what we learned yesterday. So what we talked about yesterday was the parent function of the cubic function, and it looked something like this. It had this point of inflection, or what we like to call the POI, where there was a little twist. And it translated exactly the same way as all the other functions we learned. But the thing about the parent function of this cubic function, it was very simplistic. It looked like this: y equals x cubed. And it intersected the x-axis exactly one time. It intersected the y-axis exactly one time. Pretty simple, huh? Well, I'm going to show you some more complicated cubic functions, and frankly, more fun. So let me go away for a minute. Here are three cubic functions on the same graph. Pretty interesting, huh? These cubic functions have 3 points that intersect the x-axis. At least 2 of them do. So this gold one, or this yellow one, intersects the x-axis at 3 points. 1, 2, 3. 3 intersections. That's because this does not look like the parent function. And frankly, the equation is a lot more complicated. It's still a cubic function because the lead term has an exponent of 3. So the greatest exponent in this function is 3. That makes it a cubic function. But because it has some other terms in it, besides just that cubic term, it does some really interesting things. It's got a kind of like a max here, but then it comes back down and it decides to turn around again. It begins at negative infinity, and it goes up to positive infinity. And in between, it hits a max point, hits a min point, or at least a relative max and a relative min point, and then before it goes on up into the infinity oblivion. But the most important thing we can see about this is it's got 3 points where it hits the x-axis, so there are 3 roots. If you look at this green one, there are 3 roots here also. 3 places where we can intersect the x-axis. We also call those zeros, so there are 3 zeros. Sometimes there's only 1. So like this red one. This red one begins at negative infinity, touches the x-axis, touches the y-axis, does a little twist, and goes up to positive infinity. But in between, it never really comes down and hits the x-axis again. So this is what I love about cubic functions. You really never know what you're going to get. Maybe it'll be simple, maybe it won't. So here's a factored equation of a cubic function. How do I know that this is factored? Well, if you see, there are 3 x's that are multiplied, but it's in factored form. If I was to multiply all this out, I would probably FOIL the first 2 and then multiply to the third. I would end up with an x cubed as my lead term. So it would be a cubic function. However, this is in factored form. Now, factored form may be a good thing because if I let my f of x equals 0, that will tell me where this function intersects the x-axis, when f of x or when y equals 0. So it's good that it's already in factored form. So I can make kind of a triple T out of this. If x plus 2 equals 0, well, I know one of my roots has to be x equals negative 2. If x minus 1 equals 0, I know that one of my roots will be x equals 1. And if x minus 5 equals 0, I have a third root of x equals 5. We have three roots, negative 2, 1, and 5. I don't know how that 5 got all the way down there, but you can see. Now, I typed this into Desmos, and I graphed it. And you can see, indeed, I do have 3 points where the function intersects the x-axis. I also have a point where it intersects the y-axis. There'll always be one y-intercept because of the bounds, negative infinity to positive infinity. So it needs to go through the y-axis at some point as it moves across the x domain. The domain for x is still negative infinity to infinity. The range for y is still negative infinity to infinity. But along the way, it does some interesting things. Here is a really interesting cubic function written in factored form. And the reason why I like this is because two of the factors are the same. If I make my f of x equal to 0, in other words, y is 0, I'll find my x-intercepts. But two of the factors are the same. So therefore, two of the roots are going to be the same. If x plus 4 equals 0, x equals negative 4. And x equals negative 4 twice. So we have two equal roots. But we have a third root of x equals 2 that is not equal to those. So my roots, there's only two. X equals negative 4 and 2. Now, I put this in Desmos, and I generated the graph, and lo and behold, there are only two places where this function touches the x-axis, because, or g of x touches the x-axis, because in one of the roots, there's what I like to call a bounce. The function came from negative infinity, traveled to the x-axis at negative 4, bounced off of the x-axis, came back down to its min, and then back up again to its next root of 2. So there ended up only two roots here, because one of the roots was actually formed from two equal roots. We get this from the bounce. So this bounce here gives me my two equal roots, negative 4 and negative 4. When we write these roots, we don't need to write them twice. We just write that negative 4 once. And of course, this 2 is just a single root where the function passes through the x-axis and on out into positive infinity. So the bounce will create two equal roots, which will give you a cubic function with a total of two roots. You can see the y-intercept, 0, negative 32, there will only be one. There can't possibly be two y-intercepts, otherwise it would break the rule, the vertical line rule of the function, and it would give you 2 points with an x-coordinate and two y-coordinates, or an input with two different outputs. Here I have factored form of a cubic equation, and I have one trinomial that I really can't factor any further because there's no way I can possibly get any number that would add to 6, or any two numbers that add to 6 and multiply to 10. So no two factors of 10 will add to 6. So you won't find any real roots from that. However, we do have one of the roots. If x minus 1 equals 0, x equals 1. X squared plus 6x plus 10 is not factorable, and as a matter of fact, there are no real roots. So what will this function look like? Well, we only have one root, so what might have happened? Well, when I type this into Desmos, you can see this guy tried to get up to the x-axis, but just didn't make it. So coming from negative infinity, this function traveled towards the x-axis, turned back around, went back down to its local min here, went by the y-axis at negative 10, 0, negative 10, and found its only root, the only time it intersected the x-axis, at 1, 0, before it went on up into infinity. So here, my function has only one root because the max here came up and just never got high enough to reach the x-axis. So there's only one intersection with the x-axis until it goes up into infinity. If you think about it, there has to be at least one root. There has to be at least one intersection with the x-axis if this function is going to travel from negative infinity to positive infinity. There's just no other way to do it without going through the x-axis at least once. But it might go through twice, and it might go through 3 times. Again, that's what I find so interesting about the cubic function. Here's your y-intercept, 0, negative 10, and here's your only root, 1, 0. Every cubic function has to have at least one root, but it won't have more than 3. So, cubic functions, they might have one root, they might have 2 roots if there's a bounce, they might have 3 roots if the function passes through the x-axis 3 times, but that'll be it on its way from negative infinity to positive infinity. And that's why I love cubic functions. Hope you have a great day. I hope you enjoyed the video.